Hello again, this is Wojciech Sierra Papa 5, Whiskey Whiskey Papa, and I believe my screen sharing should be fine now. So this is the second attempt to live stream my VHDL coding, because just 5 minutes ago there was problem with the downscaler for my screen, because I'm using 5:4 aspect ratio. So let's check. Nothing heard. Sorry for the delay, but I'm not sure if my screen is now visible correctly on YouTube. And I don't believe I have any means to check that. I think I'm going to assume that my stream is okay and just proceed. So hello again, this is Wojciech, and really sorry for our technical problems today. So last time, a few days before Easter, we have attempted to code. So the problem actually was not in the VHDL code. It was not in the C code. And the problem existed between the keyboard and my chair, and it was me. So let's take a look again at the spectrum. So we are back with the settings that we had before, a few days ago. And the problem was that the spectrum didn't actually look like PSK. So it resembles the PSK spectrum, but not quite. One of the things that's not actually normal is the DC peak at the center. So we actually don't want that. And let's take a look at actually what's being sent from the STM32 to FPGA. And if you remember, we've got a piece of code running on the STM32, and this actually from here, yeah, this part is executed 24,000 times per second, and it's like fetching a new baseband sample. So the baseband samples are they come from the ADC. So normally, if you want to transmit FM or AM, you just sample the signal over ADC and send the baseband samples over SPI to the FPGA. For the FPGA to do the DSP and heavy lifting. But in our case, we use the ADC as a random number generator, pseudo-random. No, actually, it's pretty random, but it's not totally random. We are using the least significant bit of the ADC to generate some random 0 and 1s. And in our case, that's the ADC underscore val. That's the value that we get from the ADC. We end it with 1, so it's either 0 or 1. That gives us this baseband sample or this baseband sample. So in our case, that was this value, 1000 in hexadecimal. And in this case, it's a negative value. So let's take a look at the spectrum again. We can see that there are two group of points in the constellation. And for BPSK, we actually expect the group of symbols, the received symbols, to be confined within the red circles that you see on the right-hand side of the screen. But if you look at the spectrum analyzer, it's the upper left corner. So there are two arcs that just switch sides from left to right. And let me check private messages on Discord. Really sorry. Yeah, so the screen is a lot better. So thanks, Morgan, for the tip. And I had to just tweak some options in the OBS. So thanks again. Merci beaucoup. Right, so we've got two arcs just jumping left and right. So the problem is we are using two values because that's BPSK. So we want to have the signal with phase 0 and 180 degrees, or pi in radians. So the signal is either sine wave or inverted sine wave, or cosine, because we don't really care about the starting phase. So we expect the signal to have two states, either zero phase or inverted phase. But in our case, there is something wrong going on, obviously, because there is a big DC peak in the center. So let's go one step back and analyze how it should look like. So if you look at the, if I'm going to draw something, I'm going to attempt drawing something. Yeah, I'm new to this software, but I hope you can see it okay. Let's start with the coordinate system. That's our I and Q plane, which is a fancy name for the complex plane. It's all the same. So for the BPSK, we've got something like this. We've got 1 point here and 1 point here. Of course, that's the in-phase and quadrature component. And 0 is, of course, at the intersection. That's the origin. So if you take the BPSK signal and like record it and look at the baseband, so long term, you get the DC component of 0 because both bits just cancel out. We assume, of course, that both bits 0 and 1 occur at the same probability. So there is no something like a long stream of ones or zeros. So for a random stream of zeros and ones, for BPSK, there should be no DC component. And in our case, we of course see that component, which is a small hint on what's going on and what's wrong with the symbol stream that we send. Actually, not the symbol stream, but the phase words. So 1000 and some negative value, F600. So something is wrong with those values. That's the hint that we get from the DC peak. Now, let's take a look at the values that we actually use. So that's 1000 and F600. So if you remember correctly from our last video, our phase accumulator is actually it's not a phase accumulator, it's a lookup table. It's 10 bits. So we've got values from 0 to 1023, meaning that for an angle of 0, we have to use value of 0. And for an angle of pi over 2, which is 90 degrees, we have to use a value of 1024 divided by 4, 256. So that should be the value to use for plus 90 degrees phase shift. And in our case, we are using a value of 1000 in hexadecimal. So let's take a look at what the corresponding angle is for that value. So let's start with this. Let's divide this. Actually, we have to right shift it by 6, just because our phase word is 16 bits, but we use only the 10 most significant bits. So you have to discard the 6 least significant. So that gives us 64. And if we divide that by 1024, that gives us this. And this is actually not in degrees, but if we do something like this, yeah, 22.5 degrees. So if we go back to our blackboard and look at the BPSK constellation, you can actually see that the angle between those 2 points is pi. So it's exactly pi. It's 180 degrees. And if we have 2 points in our constellation in the code, we know for a fact that one of them is 22.5 degrees. So it's, let me try and draw it. I suspect it's going to be somewhere like this place. And the other point is, let's copy this and let's see. So that's F60 actually, because that's not F60. Let me think. I believe that's -10. If we do simple arithmetic, signed arithmetic, and if we subtract 10 and add 1, no, we don't have to add 1. Yeah, so F6 is -10. And if we go back to these calculations, and for -10, we don't have to do this, I suppose. All right, so I'm kind of lost, but let's see. Yeah, so we had a value of 1000, which is actually 16, not -10. Yeah, so we can start with saying that our constellation is not symmetrical, and it doesn't even have rotational symmetry, because if we take a look at the BPSK constellation, we can clearly see that, oh my god, yeah, sorry, we can clearly see that you can rotate this by 180 degrees, or yeah, any multiple of that, and you end up with the same constellation. I mean, the points are not going to be, I mean, one is going to be where the 0 was before, but all the points are going to be aligned, just like the original one. So this is the rotational symmetry. And in our case, we had, let me actually try and write something here. We had a value of 0x 1000 right here, and then something lower value here, because this is, if you take a look at this part, it's 16, and that 0xf600. If you take a look at this part, it's -10. So that's closer to the I-axis. So in any case, those 2 points are nowhere close to this. So we have to actually fix that. And that causes the DC component to leak. Because if we take a look at this pair of points, we can see that the average is somewhere here. I'm not sure if I can use the word barycenter, but that's if those were masses, that would be the center of gravity. So that's the middle point between this point and this point of the constellation. So in our case, it's not 0, but we need it to be 0 to get rid of the DC component. So let's get back to this, and let's think about what the correct value should be. So for the BPSK, we want the phase shift to be 0 or 180 degrees. But in our case, we can actually do something equivalent to that. We can either set the carrier to plus or minus 90 degrees, which is going to cause exactly the same effect. So let's do some arithmetic again. And let's do it like this. We want the angle to be plus or minus 90 degrees. So that's 90 over 360 times 1024 and shifted left by 6. So you get this value. That's a positive value for positive 90 degrees shift. So let's go ahead and use that value for this phase word. Now, this one should be the same value, but negative. So let's actually do this. Hex. Let's subtract that value. Yeah, that's C000. So the least significant bits are also 0. So we can just set this value, and this can be left with 0. Okay, so we can expect the signal to actually wiggle between plus and minus 90 degrees phase shift. So if I actually try and program the microcontroller with this code, we've got the carrier, the spectrum analyzer. And after doing that, yeah, we should get rid of the DC component, and the PSK mod should be saved and it's now fixed. Yeah, so the problem was in the arithmetic, because I just calculated the wrong values for the phase words. So for BPSK, we got plus and minus 90 degrees phase shifts. And of course, we can take that one step further and try with the QPSK. So right now, if you take a look at the spectrum analyzer, we've got the BPSK decoder, and the symbol rate is, of course, 24K. That's because if we take a look here at the timer 7, that's 4,500 maximum value. Of course, -1, because it starts at 0. So if we know the clock value for that timer and divide we get 24K as the symbol rate. So that's the symbol rate, and that's the rate at which the SPI transactions happen between STM32 and the FPGA. So that's for the phase mod, for BPSK to be precise. Now we are going to maybe take a look at the netlist analyzer for the FPGA. So nothing changed here. This is exactly how it was a few days ago. So still we've got the register 12, that's seen hexadecimal, fed to phase modulator. And if we take a look at the phase mod, that's very simple. That's just the lookup table disguised as a different block. So we take the 10 most significant bits from the mod_I input and output cosine and sine values for that angle. And that's it. Yeah, so nothing changed here. We've got the register 12 used for the phase mod. And after the multiplexer, nothing interesting happens still, because we've got the digital pre-distortion set to 1. So it just multiplies I and Q samples by 1. So no changes here. The balancer is also multiplying both branches by 1, so it does nothing. And the offset just adds 0, so also does nothing to the IQ stream. All right. So what was wrong with the ADC? The DAX that we have used before. Actually, I'm not sure what happened at the DAX, because the signal there was really bad, and it didn't really look like the PSK. So I believe there was some glitch either at the DAC or in the VHDL code that handles the data transfer between FPGA and the DACs. So anyway, I have removed both of them from the board, and we are not going to look at the baseband in real time using those. So forget about the DACs for now. So before I fix that, we are not going to look at the baseband at the FPGA level. So we can only take a look at the receiver level. But that's fine. As we see at the spectrum, we've got 2 solid points within the circles for the BPSK. So let's get back to the C code, and let's actually try and transmit some QPSK. So if we switch to the QPSK demode, you can see that the 2 points just wiggle randomly, and that's because the instrument is actually trying to align the phase with what it expected to be, and that's not going to happen because there are not enough phase transitions for it to lock. So actually, let's do this. We've got the BPSK constellation set with those 2 points, those 2 values. So let's actually comment that out, both of them. Oops. I actually expected this stream to be quite short, but I'm quite verbose. I'm not a chatterbox, actually, but okay. So for the BPSK, we wanted to have 2 constellation points, but for actually, let me clean the screen by clicking this. Yeah. All right. So for BPSK, we had 2 constellation points. Oh, that's not what I want. Yeah, much better. All right. So for BPSK, we had just those 2 points at plus and minus 1, because actually the distance between those points is Normally, when you send data from some source to SDR transmitter, you are confined to some specific range. And in our case, that's 14 or 13 bits. And you have to feed a sign there too. So those values are 14 bits signed. So you can expect that the maximum value is going to be just 13 bits to the power of 14 minus 1 for the maximum value, and the minimum value is going to be 2 to the power of 14 negative, if I got it correctly. Probably not. Let's see. Let's take it one step back before we get to this. So let's actually take a look here. Yeah, so the in-phase data and quadrature data is 14 bits, but the least significant bit is always 0, as the specification says. Yeah. So the least significant bit is always 0. So that gives us that leaves us with 13 bits. So 12 bits plus the sign bit. So, okay, I'm not going to attempt and calculate the maximum range of that signed integer, but I believe that would be okay. Let's actually do it. Let's make the stream longer and thus more boring. So that's 12 bits. From 1 to 13, that's 12 bits. So 11 bits in a row. Yeah, so that's the maximum value. So that corresponds to, let's say, a positive 1. Or actually that doesn't correspond to positive 1, because you have to divide that by the minimum from the range, of the range. And the minimum is 2048 negative. So basically, we've got signal that is in this range, and we want the constellation points to be not at the edges, because when we apply filtering, we've got some overshoot resulting in the signal. So we need to have some overhead for the overshoot in the signal. So you can just set the plus and minus 1 just to the maximum and the minimum value for that range. Because if we did that, you would see some clipping going on, and that's of course not desirable, because that causes some spectral splatter and unwanted emissions. So that's not good. All right, so going back to this. So that's the constellation for the BPSK. That's 2 points left and right for 1 and 0. Now for the QPSK, we've got 4 points. And that's 1, that's 2, that's 3, that's 4. So if you take a look at the angles, it's also worth to note that in BPSK, each symbol carried just 1 bit. And in this case of QPSK, we've got 2 bits per symbol. And let's take a look at the angles that we have. Of course, that's also rotational symmetric. So if we rotate this by 90 degrees, we end up with the same constellation. Of course, the numbering wouldn't match, but that doesn't matter, at least for now, in our case. So let's take a look at the angles that we have here. So that's 45 degrees. That's pi over 4. And this is 135, if I remember correctly, because that's 90 plus 45. Yeah, that's 135. So how to get those values into phase words that we require? So let's get back to the calculator and let's do this. Let's divide 45 by 360. It's going to give us the ratio, and multiply that by 1024. And of course, we need a shift of 6 bits, because the most significant part of the word is actually the part that's going to the lookup table. So that's 2000 in hexadecimal. Oh, I actually have those values already punched in. I just need to uncomment those. Yeah, so that's for positive 45 degrees. And if we just multiply that value by 3, because we've got 45 here, 45 degrees here, and 45 here. So this tuning, this phase word times 3 is going to give us this one. And it's already done for us. And for the negative values, for 2000, we've got A000. And let's check if that value is correct. I suppose it is, but, well, better safe than sorry. 2000, yeah, 2000. So let's subtract, caps lock, sorry. Let's subtract, yeah, so those values are swapped. So let's just swap them again. Yeah, so for 45 degrees, we had 2000. For 135, we had this value. Then for negative, actually, when we talk about positive and negative angles, I might not be sticking to the convention, but it doesn't matter in our case, because we are probably not going to use row DQ row QPSK, but instead we are going to use DQPSK. But whatever, those values are not really relevant, and we don't care if the phase shift is positive or negative. So we just want the constellation to be filled with sample data points. So we've got 2, we need 4. Let's go ahead and add those 2. In our case, let's say that's minus 45 degrees, and this one is minus 135 degrees. So if we run this code now, we should see the spectrum analyzer that all 4 points are populated with sample points. And that's the case. Yeah, so it works. There's some strange thing that's going on in the constellation, because if you look closely, the points in the constellation, they just jump. It's like something like a bistable constellation. So we are not getting a perfect square, but instead we are getting a rectangle in 2 different aspect ratios. So we've got 2 aspect ratios for the constellation, just going back and forth. And I'm actually not sure what causes that, and I suspect it's some timing issue between the FPGA and the 8086 RF chip. Because as far as I know, the lookup table is constant. It should be. And that shouldn't cause anything similar to this. So if this was a perfect setup, we would have just 4 points at the, what's the plural of apex? Apices? No. Apexes? Anyway, we would just end up with a square, not a rectangle, not a jumping rectangle. All right, so if this works and if BPSK works, oh, it's also important to note that the baseband is a staircase, so it's not filtered. We actually send it. I mean, the baseband is just 4 values, and there is no like a smooth transitions between all those samples. So we just send the one value, then the other, then next one, and so on and so forth. So we don't actually apply any filtering. If you take a look at the spectrum analyzer, there is the filter setup that the instrument can be actually told to filter the baseband. We actually told it to not to filter it because we expect the signal to be just staircase. But the next step would be to apply some root raised cosine filtering for the baseband and actually use this. So if you apply unnecessary filtering at the receiver side, you can see that the eye is closing because you've got the filter adds some modulation error ratio that actually it's being measured by the instrument. It's 22 dB, and hopefully if we turn the filter off, we should get a better value. That's 30 dB for the MER. Yeah, so if that stuff works, the next step would be to filter the baseband, probably also try with the differential PSK, and maybe also with the pi/4 DQ PSK that is used in Tetra. And probably that's it. So the problem was between the keyboard and the chair. So the VHDL code is published on GitHub, and the repository name, I believe, is OpenHT-FPGA. So the code is updated, and you can take a look at actually not the main, but all the files that are lower level. So the top level VHDL file is not yet published, but this only governs the interconnections between all those blocks. So all those blocks are already available for download in VHDL, but the interconnections are not yet available. So you have to give us a few more weeks to finish this stuff. Yeah, so BPSK works, DQPSK, QPSK, sorry, works, and the bug is fixed. So I think that's it for today. I hope you're not asleep. And if you are, it's time to wake up, grab a coffee. All right, so see you guys later. This was Wojciech, Sierra Papa 5, Whiskey Papa from the M17 project in the M17 Labs, Poland in Europe. Yeah, so 7-3, and see you next time, guys.